Alright guys, so for this video, I'm going to be showing you how to do an aimbot with some smoothing. For this, we'll be using two different methods for choosing targets, where one is going to be the closest angle or the closest enemy to our crosshair, which in this case would be Lois. The other one is going to be the closest entity or the closest enemy to us, which would be Francis in this case, even though we're aiming at Lois. This is just two different ways of prioritizing targets. But of course, both of these methods are going to take into account that they're actually on our screen or in our FOB. So we're not going to be aiming at anything or snapping to anything behind us. Now we pretty much have everything we need except a way to modify the player's view angle, since the one in the player class we found doesn't seem to be writable. So we'll have to find a different pointer to that. But anyways, if you just found this video randomly, this is part of a series, so I recommend you watch that first. Alright, so let's actually find that writable view angle. So if I remember correctly, in the first couple videos, we actually found the view angles, but when we wrote to them, they didn't actually reflect in the game. So somewhere in here, I didn't actually mark them down because they weren't useful, but we can use those values to actually find the real value. It should be right around here. It's probably these four, even though they're completely the same. So if we move this to the side, if we look straight up, straight down, and across, it seems to be our view angles. When we actually write to them, it doesn't reflect. So what we'll do instead is we'll open Cheat Engine, and we'll scan for those values we see there, and try to find the actual value and not a copy of it. Let's make float 9.074, move a bit up, and what does seem to be inverted, as in when I look up, it gets more negative. Normally, in most games, when you look up, the pitch gets more positive. But I think with most source games, it's inverted for some reason, where looking up becomes more negative. So we'll have to remember that when we actually write the code. Anyways, let me put negative 58 for the next scan, move it a bit, and let me keep scanning for a bit. Alright, so I scanned a couple more times and I couldn't get anything below 402. So we're just going to do a bit of testing here. I don't think it's going to be any of these static pointers because normally there's no reason for the yaw or pitch to be its own global variable. It's probably part of some other bigger structure instead. So I'm not even going to try those directly. So what we're going to do is I'm going to highlight half of these. I'm going to click this one, hold shift, and go halfway, change it to 90. It doesn't seem to change, so we'll delete it. Do the same thing, do 90. It's the bottom half, so we can delete the top half. Just doing a binary search here, basically. 0, so it's the top half, and we keep doing that until we get to a couple. Some of these, 90, delete that. Sometimes you're going to be careful with this because if you change too many values at once that aren't actually the yaw or pitch, it could crash your games. Don't do it when it has like a couple thousand. Here's our value. Now let's see if we can find a pointer to this. So if we can find a pointer to the pitch, we can just add 4 and get the pointer for the actual yaw, hopefully. So let me see what accesses this address and see what structure it's part of. So we have EAX plus whatever that hex value is points to our float. So what we can do is we can find a pointer to EAX, and then when we're dereferencing it in the code, we can just add 400 or whatever that value is to get our pitch. This is usually a bit more consistent than trying to find a pointer to this directly. Instead, we find the pointer to the structure that holds our pitch and then add the offset afterwards. So we add that address, pointer scan for this address. Let's do a max level of 3, and let me let this scan for a bit. All right, so here's what I got. I did change it to a level 2 pointer because 3 was taking forever, which was a good idea because I ended up with a level 1 pointer. We're going to use this one because it's the smallest one and in lines with the other pointers we found. Okay, so let's use this in our code. And I think this is the perfect time to actually show you guys a different way of reading pointers. So far, we've been reading multi-level pointers by hand. So for example, with our view matrix pointer where we have our base address and this offset, we've been doing this in 2 lines. But eventually, if you have a level 4, level 5 pointer, which you really shouldn't, because they're usually not reliable. But if you did, it would it would be a pain to read it line by line. So instead, what we're going to do is we're going to store it in an array. Now you might have seen other people store it in an std vector instead, which I don't think is a good idea because it doesn't allow the compiler to optimize as much as it can. So instead, what we're going to do is we're going to store it into an std array using a constant expression. Constant expression basically tells the compiler, this is never going to change, optimize it as much as you can. So an std array, the type that it's going to be storing is an std uint32t, and the size I think is 2, and let's call that offsets or offset pitch. And it's going to be equal to the first offset, which is 042, whatever that is. And the second offset was 8. Now remember, we did say that this is the pointer to the base structure that holds the pitch. So we're going to have to add that offset we found when we access the class. So I think I still have it open somewhere in here. If you go find what accesses this address, and it's not that one. We still have to add that to it, which is 4AA4. So we do 0x8 plus 4AA4. Make sure you put 0x after everything, otherwise it's going to interpret it, mess up your calculations. And this should be a 3 because it's 0 indexed. And we also need to include array. Now we're just going to copy this, and instead of 8, we're going to add 4 more bytes because an integer is 4 bytes. We go to the next offset down here. So if this is pitch, we add 4, and we should get to yaw, hopefully. And that should be C instead. Of course, this could be in one line, but I'm just being lazy, and we can just leave it like that. The compiler will deal with that for us. Now we're going to need a couple new memory functions to actually read this array. So let me go to our memory handler.h, go to our template. We're going to have a private function, which is going to be resolving the address itself. So it's going to be template, and it's going to take an std size t of n. I'll explain what that does in a second. It's going to return a pointer, and it's going to be resolve pointer chain. In it, we're going to have an std array of pointers of that size n, and let's call it offsets. Now if we go back to our offset, so you can see when you're declaring an array, you also have to pass the size. In this case, it's 2, 0, and if we go back to our memory handler, so basically this template makes it so the compiler can make a function for us no matter the size of the array that we pass. Now this function is going to be called by 2 functions, which are going to be 2 overloads of our write and read memory. So let me make some space here so it's a bit more clear of what we're doing. So we have our read memory and our write memory. We're going to overload it, so it's going to have the same name but different parameters. So it's going to be template type name t, which is the type that it's actually returning, or what we're actually reading, and the size of the array we're passing in with the offsets, which is going to be size t. And then before I forget, make sure you include array here. Now it's not going to give you any errors or red underlines, but it's going to give you a runtime error. So make sure you have that. So this read memory function is going to take, or it's going to return the type that we're reading. It's going to take the base address, which is basically going to be either client DLL, engine DLL, or server DLL. And it's going to take that std array of offsets. So basically we can do the same thing for the write memory. We can copy this template and do bool write memory. We can copy all of this, paste it in, and the last argument is just going to be the actual value. All right, so let's go and let's do the resolve pointer chain first. These are all going to be relatively simple. First, we're going to actually check that we have offsets in it, just so we don't crash for absolutely no reason. So if offsets was empty, we just return -1. Now we're going to do a for loop. We're going to start at 1 because the first offset is the base address. Then we're going to do I such that offsets that size -1 because we're starting at 1, so the length is 1 less. And we're going to do I++. In here, we're just going to read process memory. of the interprecast of the base address, which we did not make, which should be std uint32t. Current address is equal to offset 0. So the base address becomes the first address we read from. So we interprecast of that weird address, the address of that current address, the size, which is going to be the size of current address, which is the size of uint int 32t, which is 4 bytes, and null pointer. And then we can just add the current address to offsets.i and go through the loop again, and then we just return the current address and we finish reading all the pointers. Okay, and that's pretty much it. These two are relatively simple. Again, I am going to do this sanity check just in case. We're going to set the first offset to be the base address. Offset 0 is equal to base address plus offset 0. So our base address would be engine DLL. The first offset would be, where is it? The 04, whatever that is. And then we're going to pass that into our function to read through all the offsets and dereference them, and then return the final pointer. So now we're going to call that function. So uint32t final address is equal to resolve pointer chain of offsets. If the final address is equal to -1, like we return down here as an error, and then we just return false. Otherwise, we can just return write memory of t using that address and the value itself. And we can pretty much copy this and do the same for read memory, but just change the last step to be read instead. Make sure it's the same arguments, and I think that's correct. I guess we'll see when we actually test it. There's probably a typo in there somewhere. So now we can go to our offset handler and make two functions. One to set the view angles, float yaw, float pitch, and we can have another one to get the angles. I guess we don't really need this function because it's in our player class, but just in case they're not always matching up, we might as well get the one that's probably going to be the more accurate out of the two, the one we can actually write to. And this is going to return by reference. So we can actually return two things at once. So now we can just simply do memory handler, write memory, the type is a float, the base address is the engine base, the offset list is offsets yaw, and we make sure to actually rename one of them to be yaw. We can copy this, paste it, pitch, and pitch. Now we can go and do the same thing for the other one. All right, there we go. Now let's actually make the aimbot. So there's a couple of changes we need to make here. Well, not a couple of changes, just a couple of things I want to add here. Of course, we're going to have to forward declare aimbot. So let me add that real quick. And we're going to have one more thing, which I like to do for just the visual effect. We're going to store the current target of the aimbot in the CheatManager class. So in the ESP or any other class that might need a target, they can use that instead of having to recalculate it everywhere. It's also going to make it so in our ESP we can do a little visual of our current target. It's going to be really nice for debugging. So it's going to be an std shared pointer to an entity, and let's call that current target. Now, because this is a shared pointer, even if the vector or the entity inside the entity list gets deleted, I still have a copy of it, so I'll never run into any ownership issues. And because of that, we're going to have to make a small change right here in our memory handler for reading arrays. Where is it? Read pointer array. We're going to add one more thing. It's going to be bool reset vector, which is basically going to make it so every time we repopulate the entity list, we don't delete all of those shared pointers immediately. Instead, we just copy the data into them, or delete the pointers that we're not using instead. I'll show you what that means in a second. Whoops. Let me copy and paste this. I just realized we never actually used this check permission variable here. And I guess I'll fix that. So for reset vector, we're going to vec.clear. Instead of emplacing every single time, what we're going to do instead is we're going to check if I is less than outlist, not outlist, vec.size. We're going to dereference it, so vec.was equal to object, so it's going to copy it inside. Otherwise, if we haven't made that pointer yet, we're actually going to make the pointer and put it in the list. And let's use that check permission that I've never used, which should be here. Surprise, no one said anything. I guess we've been using it this whole time. Change that to true, so it doesn't break anything. Anyways, we go back to our CheatManager. We have our current target. Let's go to our constructor and make sure we add the aimbot here. Aimbot, and here we go. It's the same as the other, and we're just passing the current target or reference to that current target in the aimbot constructor. The aimbot is also going to have two functions, which let me make them real quick. Let me add a new class. Let's call it aimbot. I don't think it's even going to get put in the folder. I don't know why it does that sometimes. In here, we're going to have a couple functions. First, we're going to have an enum, before I forget. That's going to hold those targeting methods. For now, we're going to have two. We might add more later, depending on what in-game functions we find that we can call externally. But for now, we can only do two. Closest angle, which is the closest thing to our crosshair, or the closest distance, which is the closest thing to our actual player. You can name these whatever you want. Just make sure they're used in the same way. We're going to need ctime, we're going to need vector, and memory. And we're going to need a forward declaration to the offset handler, because we're going to have to pass that in as well. So the public, we're going to have the actual aimbot constructor, which is going to take that shared pointer reference that I was talking about. And we're also going to have to forward declare that as well, before I forget. We're also going to need set window offsets and set window sizes, just like the ESP, so the aimbot can draw its own FOV circle. Honestly, the FOV circle is not that visually pleasing, but it's really nice for testing. And actually, I'm just going to go to esp.h and copy this exactly. And then we're going to have a couple private functions. Oops, I'm missing one, which is run. I'm just going to take the offset handler reference to the offset handler, the player reference to the local player, a constant std vector to the std shared pointers of entities, reference to entities, and the view matrix, so we can actually draw with it. And here in the private, we're going to have a couple things, the actual aimbot settings, and some things for smoothing. So we need a boolean for enabled, boolean for actually smoothing. Let's set these to true and false by default, or both to true. The smooth amount doesn't really matter. I'm going to set it to 0.1f for now. Another boolean for the FOV check, so that's true. The FOV, which is going to be the range of what we can actually shoot in, which is in pixels. It's not crazy math or anything, it's literally just pixels. And we'll draw FOV circle, which is basically just for testing. We want a vector 3 for the center screen position, int for the window width, window height, the offset x, and the offset y. Then we're going to have one more for the current aim time, which basically stores how long we've been aiming in that specific entity. The clock t, which is last aim time, how much time has passed since we last aimed at that entity, and the std shared pointer to that current target, and of course the targeting method, which by default I'm just going to set to the closest angle. And let's do method, not methods. And we can include that, and we can forward declare the player as well. And then we're going to have a couple more private functions. We're going to have the smooth angle function. We're just going to take a vector 3 reference to from, constant vector 3 reference to where we're aiming, and the percent, which I'll explain what that does when we actually write the function. And we also need one more, which is the targeting system, or the targeting function, which is going to return that entity that we're targeting. We'll call it getTarget. It's going to need a player reference to the local player, the entities, and the view matrix. Basically just the same. Okay, so let's start by the getTarget function, which is probably going to be pretty simple. It's going to handle both targeting methods in one, but eventually if we add more, depending on what functions we find in the game that we can call externally, we might have to separate this function into a couple different ones. So by default, we're going to have a shared pointer to an entity. That's going to be the closest entity that we find. It's going to be null pointer. The closest distance is going to be very big. I'm just going to set it to 999.5 or whatever, 0.0f. I know there's a constant for it, I can't remember what it is though, so I'm just gonna make this a really big float. The distance, the current distance is 0 and a vector 3 for the screen position. Now we're gonna iterate through all the entities. And for this, we're gonna use a constant auto reference. Make sure to use a reference here so we don't make a copy of the entity every single frame. Now we're gonna do a small sanity check just to make sure the entity is valid before we try targeting it. So if the entity health is less than equal to 0, or entity position.x is bigger than equal to a very big number, then we could just continue. I'm only checking for 1 because usually if 1 is wrong, then all of them are going to be wrong. And I'm getting an error here because I didn't fully define these variables, so they're incomplete types. So we need to include memory handler, and offset handler. Now we're going to get the head position of the entity so we can actually find out which entity is closest to our actual cursor. So if we go to the game, we need to find our actual world to screen position so we can compare that to our center screen position and find the nearest one. So the head position is entity position plus vector 3, 0, 0, 20. Now we can do screen position is going to be equal to directx world to screen. We're going to pass the head position, B matrix. It's very similar to the ESP. Window width and window height. Now you might be wondering, if this is so similar to the ESP, why are you making it its own function? Well, eventually it's not going to be similar. Eventually, when I do find bones for the ESP or for the aimbot, this targeting system is going to get a lot more complicated, and it's worth having its own class for it. For now, it's very simple, but it's going to get more complicated when we add bones. Now we're going to add the offset as well. This equals offset x, which is the offset of the screen. Of course, we're going to have that sanity check like we did in ESP, and we're going to check if the screen position dot z, and remember, z in screen position is basically the depth. So if the depth is behind us, or that is not visible, so we continue. And now we're going to check if it's in our FOV. So if we are doing the FOV check and the absolute distance of the center screen position, distance to the screen position is bigger than the FOV, that means it's out of the FOV, so we continue. Now we're going to choose our targeting method. So if the targeting method is the closest angle, which is the closest entity to our crosshair, then our distance is going to be equal to the absolute distance of the center screen position to the screen position. Otherwise, since we only have 2 targeting methods, we're just going to use an else here. The distance is going to be the absolute distance of the player position to the entity position. And now we can just check if the distance is smaller than the closest distance is equal to the distance, and the closest entity is equal to the entity. Pretty simple. And make sure we return the closest entity as well. Okay, so let's do the other function. Let's actually do the aimbot logic, and then we'll do the smooth angle right after. And actually, let me do this so I don't forget, which is going to be very simple. There we go. Now let's do the actual aimbot. First, we're gonna have to start by actually drawing that FOV circle, even if we're not pressing our aimbot key. So if draw FOV circle, we're going to MGUI get background draw list, add circle, pass the Aimbot2 to the center screen position. The FOV, the color, which I'm just gonna make it red, I think. The number of segments, which is basically how smooth circle is. I think if you pass 0, it's just a perfect circle. If you pass any other value, it's going to try to like use lines instead of a smooth circle instead. And the thickness, let's just pass 1, which is the default. Okay, the actual logic now. So if not enabled, or we're not pressing the shift key or whatever your keybind you want, async key state bk shift, or the entities is empty, we're going to return. Now I know that you can manage the keybinds in your overlay as well. Honestly, that's a pain. It's usually not worth the effort. So I'm just going to have it as get async key state for now. But eventually, if I do turn this into a kernel cheat, this would be an external call to that. You also might be wondering why for all my if statements, or I usually try to avoid doing brackets like this and just do the opposite and return or continue. It makes it a lot simpler, because otherwise we would have like a for loop inside a for loop inside an if statement, and it's going to get very convoluted very fast. But if you try to do the opposite and just return or continue, it makes it a lot simpler and a lot easier to read. So I highly recommend you do that as well. Actually, this shouldn't be return. Well, it should be, just we need to set a few things first. So if we're not aiming, or the aimbot isn't enabled, we're going to set the current aim time, because we're not aiming at the moment. We're not smoothing or anything, back to 0. We're going to set the last aim time. Actually, we don't have to set the last aim time to anything here. And we're going to set the current target equal to null pointer, because we're not aiming at anything. And then we can return. After that, we're going to do std shared pointer to entity to target is equal to get target, that function we just made. We're going to pass the player, the entities, and the matrix. If we didn't get a target because nothing's in our FOV or everything's dead, then we're going to call current target.reset and return. And I just realized I have two different ways of dereferencing a pointer. Current target equals null pointer and current target.reset are the same thing in a shared pointer. So we can just do this as well. There we go. Now, if the target we had is not equal to the current target, so if we were aiming at something and then all of a sudden another zombie comes right in front and we switch targets, we're going to reset our current aim time to 0. We're going to set the current target to the new target, and we're going to set the last aim time to now, because we just started aiming, which is clock. Now we're going to do some math here. I'm going to set clock t now is going to be equal to clock, because we want the time right now. The current aim time is going to be equal to a static cast, of a float, and we're casting it to a float because we want to be able to get a decimal. Otherwise, we'll get an integer, because clock t's are integers. They don't have floating point by default. So if we don't cast it to a float, it'll get truncated to a 1 or 0 or some weird value. So how much time have we spent aiming is going to be equal to now minus the last time we aimed over clocks per second, which is based on your CPU. So make sure you use this macro and not 1,000 or some random predetermined value you set. Now that we've done that, we can reset our last aim time to now. And now we're going to calculate a percentage of how far we should be aiming at our target. So here I'm going to make a small little graphic. So imagine our start point is where our crosshair is, and our end point is obviously where we're aiming. So in our percent is how far along we should move our view angles based on how much time we spent aiming at that target. So here we're taking the current aim time and setting it equal to the now minus the last time over clocks per second. Then what we're going to do is we're going to set that percent equal to the minimum of the current aim time over how much we want to smooth by. And we're going to cap that out at 1 just to make sure it doesn't go over. So basically what we're doing is, depending on how long we've been aiming, we're going to slowly move or increase this percentage to slowly get closer to our target. Now, this logic that I'm doing here will work for any type of smoothing you want to do. So if you want to do some Bezier curves or some fancy non-linear curves, you can definitely do this the same way using this logic I'm writing now, and then you just need to change the smoothing function, which I'm adding later. Now personally, I think a linear approach looks the most human to me, and I've never had issues with it in other projects, so take that as you will. But if you want to do some fancy smoothing, go for it. And that's pretty much all of the logic. The rest is just calculating the angles. Now we're going to set a vector 3 to the current angle. We're going to call our offset handler with the view angles. Now there's one thing I need to make sure that we don't forget is that our view angle, not our view angle, our player and our player camera are not at the same place. Somewhere in here, because I remember we tried changing it before. Here it is, 62. I don't know why it's velocity. But this value, their Z value, which means our camera is, I think, behind us or a bit above us. So we need to make sure we offset our position by 62 pixels or 62 units, whatever they use in this game. So if we go here, we go vector 3 target head is equal to target dot position minus vector 3 0 0 20. And now our vector 3 player head or player camera is going to be the player dot position plus vector 3 of 0 0 dot 62, just to make sure we offset that correctly. And now our target angle is going to be equal to calculate angle, calculate the angle between the player camera, the target position, or the target head. We're not inverting the yaw because that seemed normal, but we are inverting the pitch, so that's true. And I'll show you what I mean, just in case you forgot. You go back to our game, not that, this. And we look at our V angles. When we go up, our pitch gets more negative, which means it's inverted. I think most source engines act like this for some reason, which is really weird. And it's a pretty simple function too. We're just doing a10 of delta y of delta x, where delta is just the target minus the origin. And for the pitch sign, or for the pitch, we're doing delta z over the distance. And now we're actually going to do our smoothing. So if smoothing, we're going to check if the percent is bigger than equal to 1. If it is bigger than equal to 1, we're going to set the current aim time to 0 just to make sure we reset it. And we're going to set the percent equal to 0. And then we're going to call smooth angle with the current angle, the target angle, and the percent, which is how much smoothing or how far along we should be along that current angle. And this should all be in a bracket. Otherwise, if we're not doing smoothing, we're going to set the current angle equal to the target angle and just snap to it. After we do all of that, we're going to call offset handler view angles to the current angle dot x and the current angle dot y. Now we can go back to our aimbot.age and declare or define our smooth angle, which is honestly very easy. We need to calculate delta, which is equal to 2 minus from. I keep doing the thing where I keep changing when I use a vector 3 this way and vector 3 with all capitals. Anyways, then we're going to normalize the angle, delta dot normalize angle, and the range of that is going to be negative 180, 180, negative 90, and 90. And I'll show you what I got those numbers from. So if we open Left 4 Dead 2, we open our reclass, you can see that the max pitch we can go is negative 90. The minimum pitch is 89, or backwards because it's inverted for some reason. And the yaw, the minimum it can get to is negative 180 and 180. So that means we don't want anything above that or below that. So we need to make sure we snap back to it. We'll roll around to the other side if we get to that. Once we do that, we're going to do from.x plus equals delta.x times the percentage. Now, if you were wanting to do some other type of scaling that wasn't linear, this is where you would do it. You would change this from being a linear representation to some fancy formula. But honestly, I think this is the most human looking smoothing you can do without going too crazy on it. Bezier curves just look weird. They don't look human at all. Some of the other ones just look too precise. After that, we're going to normalize the angle again, so we can just copy this, just to make sure we don't break the game by having angles that are way too big or way too small. And let me show you what this function actually looks like. So basically, if the angle is bigger than 180, it's going to subtract 90 so I can wrap around to the other side and take the closest path in the circle. Anyways, I think that's pretty much it. It's probably one or two functions we're missing. No, nothing's missing here. Anything in our CheatManager? Actually, there is something we are missing. Our settings menu. We're going to actually fix our settings menu because I think this video is shorter than the other ones, so we might as well take that time to make sure we can test everything out correctly. Draw settings, and what I'm going to do is I'm going to make a tab bar for everything. I know some people like having different IMGUI menus or little boxes for it individually, where you have one menu on the left that's just the aimbot menu, and then you have a menu on the right that's just the ESP menu, and you can move them individually. I think that gets kind of convoluted when you add a bunch of cheat features. So what I like to do is just have one menu with a bunch of tab bars. And if you don't know what I'm talking about, you'll see. I think this is a bit easier to handle or to manage. So if not begin tab item, let's call it aimbot, return. I'm going to do all the settings. You guys should be familiar by this by now, so I'm not even going to go over it. This is just the settings we have with some checkboxes and sliders. And then we're going to add one more, which is going to be the fancy one for selecting the targeting system, which is IMGUI text. Do select targeting system. I'm going to do an if statement. So if IMGUI, I'm going to do a radio button. I'm going to make it so we can only select one at a time, which is easier when you only have two, but once you have 3 or 4, it becomes a pain. So if 3D targeting, wait, why am I calling it 3D targeting? Closest density, and targeting method is equal to closest angle. So if we click that button, we're going to set the targeting method equal to the closest angle. If the targeting method is not equal to closest angle, it's going to disable the button. Just to make sure we can't enable both at the same time. Now we're going to do the same thing, but for the other one. And now I think that's it. And make sure you don't forget end tab item. If you see an IMGUI menu item that has begin, make sure you end it with an and. Otherwise, you'll have a bunch of IO errors, which means it either is going to mess up your mouse, your input, your controller, or your menu will just look really off. Okay, we're going to do the same thing for our ESP, which we only have 2 things for now, but we're going to have the same begin tab item as well. We just copy and paste this, ESP, and end tab item. Then we can go to CheatManager, CPP, go to our draw settings and change it a bit so we can handle that. I'm going to add a bracket here, and we're going to make a new tab bar. If IMGUI begin tab bar, and this doesn't really matter what name you put here, it's not even going to show up. Just make sure it's unique and you don't use this name for anything else in the IMGUI context. I mean, in aimbot settings, and we also need to make sure we include the aimbots. And we have to, I'm going to copy this, paste it, copy aimbot, and make sure we do that same thing for the aimbot as well. Now I did want to add one more thing, which is highlighting the person we're targeting in our ESP, which is going to be really, really simple. All we have to do is go back to our CheatManager and add one draw ESP, and here we're just going to pass the current target here. And we go back here, copy this so I don't have to rewrite that. Go to esp.h, paste that in, pass it by reference because we don't want to make a copy every single frame. Go to esp.cpp, make sure we add the same thing here. And let's make a color for it. I'm color pointer to target color, and I don't know what color I'm going to do for it, but maybe blue, red, green, blue. So 255 here, and copy and paste this and add target color. And here in our ESP, we can just have a simple check. So let's do I'm color pointer to entity color is going to be equal to the entity equal to the current target, do a question mark, target color, and enemy color. So basically what this is doing is if the entity is equal to the current target, we're going to use the target color just as the true slot. If the entity is not equal to the current target, it's going to go to the false slot, which is the enemy color. And paste that in there. And I think that's all I wanted to do. I might be missing something. I guess we'll see when we run it. We already have a couple errors. We'll fix that. Ooh, we have a couple. I casted this the wrong thing. I'm missing a comma here. Or not missing. I put an extra comma when I copied and pasted, which is why you don't want to copy and paste too much. Use of undefined type aimbot somewhere. We run the code again after I fix those errors, because sometimes errors are... Okay, that makes a lot more sense. Okay, so here's one of the errors. I'm using write memory, which returns a bool, and I'm returning -1. This should be false. And I was overthinking it. It should be LP void. And then we have one error, which is static assert failed, which is can't delete an incomplete type. That means we're missing an include somewhere with our for declarations, especially with our shared pointers. All right, so the error was that I was missing include aimbot.h here, and I'm also missing we never ended the tab bar. So make sure you do that so you don't run into any errors like I just did. Hopefully that works. And of course, we also have to go to our CheatManager.cpp and actually run the menu or run the aimbots, because obviously it's not going to work. And pass the stuff it needs. So offset handler, player, entities, and the view matrix. Missed a couple things here. Remember why this shouldn't be here now. We're going to set that, and we set that. Set window sizes. When we set the window sizes, we need to, of course, set the window height equal to the height, and we need to set the window width as well. But we also need to set the center screen position, which we never did, which is just both of those divided by 2. So we take the window width divided by 2, and we add the offset x, which is basically where the window actually is. We also need this one, do that, and we also need to set the offset x equal to x, offset y equal to y. All right, and one last thing, I think, is that I flipped the yaw pitch. I found the pitch first, which was on 8, and not the yaw, which was messing things up. All right, so I ended up taking off the target head calculation I had here, because it seemed to be completely off, but it just didn't look right. So now I'm using the player camera like originally intended and the current target position instead. Also make sure that when you're reading the pointer array, we pass in false here and then true, because we don't want to reset the vector and reset all of our targets every single time we read our targets or the entity list. So now if I remove all the breakpoints I had, it should work now. That only took me forever and a lot of debugging just to find out I forgot to pass one optional parameter. But anyways, it smooths now. The targets seem to be correct. Let's try closest distance. Which, anyways, let's give it a try. And be stop 0, I think. I guess the ESP doesn't work with those enemies. And it seems pretty good. If only I had faster fire rate, but what we need now is a visibility check and maybe visibility check mostly, and some way of changing our weapon stats. Anyways, that's gonna be it for this video. Hopefully that didn't take too long. Hopefully you learned something, and give me suggestions on what else I can add. For sure, I'll add the bone ESP if it's not too much of a hassle. But besides that, I don't really know what else to add. So give me suggestions. But anyways, peace.